Our map of the cosmos is being redrawn faster than ever before. Powerful new eyes on the sky, from space telescopes to vast digital surveys, are uncovering wonders that defy our textbooks. This is a tour of the 25 most startling new space phenomena, each one a fresh piece of a cosmic puzzle we are only beginning to solve. By the end, you will witness the universe not as a static backdrop, but as a living, breathing, and often violent arena of constant change. We will see black holes on the run, galaxies that should not exist, and signals from the edge of reality. How many of our fundamental ideas about space are about to be overturned? The first discovery on our list feels less like an addition and more like a subtraction from the darkness. It begins with a region of space so profoundly empty it has earned the name the Great Nothing. The Boötes Void is a spherical chasm in the cosmic web, a staggering 300 million light-years across where almost no galaxies exist. For decades, this void was a monument to absence, a place where the universe's usual rules of congregation seemed to have been forgotten. Then new eyes peered in. Ultra-sensitive instruments designed to capture the faintest whispers of light scanned this immense nothingness, and they found a whisper. Nestled deep within the void, astronomers have now confirmed the existence of a faint, isolated galaxy. This is not a brilliant spiral or a bustling cluster, but a lonely, primordial sort of island. Its significance is monumental. Finding any structure in such an extreme environment challenges our models of how galaxies form. We thought they needed the dense, crowded neighborhoods of the cosmic web to gather enough material to spark into being. This solitary galaxy, however, seems to have built itself from the meager scraps of an almost perfect vacuum. Its very existence suggests that star formation can occur in the most impoverished corners of the universe, given enough time and a stubborn pocket of gas. Studying this lonely resident is like finding a single, carefully tended plant in the middle of a desert. It forces us to rethink what is necessary for life, cosmic or otherwise, to take root. What other secrets are hiding in the voids, waiting only for a sensitive enough instrument to reveal them? Yet the greatest cosmic puzzles are not always found in emptiness, but in the intricate dance of celestial bodies. Far beyond our solar system, a gas giant named Kepler 1708b orbits its star. Astronomers studying its light noticed something peculiar. As the planet transited, blocking its star's light, the data showed a second, much smaller dip in brightness. This secondary signal, a faint echo of the main event, is the telltale signature of a moon. They named this candidate Kepler 1708bi. What makes this potential exomoon extraordinary is not just its detection, but its inferred character. The data suggests it is a large, Neptune-sized world, a gas giant moon far more massive than anything in our own system. More tantalizing still, analysis of the light filtering around it hints it could be enveloped in a thick, extended atmosphere. Imagine a moon with its own sky, its own weather, a world wrapped in a shroud of gas while it orbits a giant planet that orbits a distant sun. Confirming an exomoon is incredibly difficult. The signals are minuscule and other astronomical phenomena can mimic them. Yet this candidate is one of the most promising we have because the signal is clean, it repeats, and the proposed model of a large, puffy atmosphere helps explain the specific shape of the light curve we see. If real, it shatters our notion of what a moon can be. We are no longer just looking for rocky spheres like our own, but for entire categories of worlds that orbit other worlds. The search for life has always focused on planets, but what if the most habitable real estate in some star systems is not a planet at all, but a moon with a sky of its own? But sometimes the universe does not hide its mysteries in lonely voids or around distant planets. It paints them across the sky in impossible dimensions. This brings us to the third discovery, a phenomenon so strange it was named exactly for what it is, odd radio circles, or ORCS. They were first spotted by the ASKAP radio telescope in Australia, a facility designed to map the sky in unprecedented detail. What it found were perfect, ghostly rings of radio emission, hanging in space like cosmic smoke signals. Their scale is almost incomprehensible. Each ORC is so vast it could comfortably contain an entire galaxy within its circular boundary with room to spare. When astronomers first saw them, the reaction was pure bewilderment. They checked for instrument error for known objects like supernova remnants, but nothing fit. These were not the messy aftermath of a star's death, nor the energetic jets of a black hole. They were pristine, symmetrical, and utterly enigmatic rings, visible only in radio light and invisible to optical telescopes. The leading theories to explain them are as dramatic as the rings themselves. One suggests they are the titanic shockwaves from a catastrophic event, like two galaxies merging in the distant past, sending a spherical tsunami of energy through the intergalactic medium. Another proposes they are the final, fading echo of a quasar eruption, a belch of energy from a supermassive black hole that has since gone quiet, leaving only this immense bubble as its tombstone. Yet for every theory there is a complicating detail. Why are they so perfectly circular? Why do we see so few of them? The true nature of ORCs remains one of the most hotly debated puzzles in modern astronomy. They are cosmic graffiti, a message spray painted across the heavens in a language of radio waves we have only just begun to notice. And their silent, giant presence asks a humbling question. What other colossal structures are we missing simply because we have not been looking with the right eyes? The perfect symmetry of those radio rings suggests a single, explosive origin. But what if the most violent events in the universe do not create symmetrical echoes, but instead send the perpetrators fleeing the scene? This leads us to the fourth discovery, a cosmic chase captured in stunning detail. The Hubble Space Telescope has spotted a supermassive black hole, an object with the mass of 20 million suns hurtling through intergalactic space. It is not drifting silently, however. Behind it, like the glowing wake of a ship, stretches a brilliant trail of newborn stars. The image is almost poetic in its contradiction. A black hole, the ultimate consumer of light, is paradoxically creating it. The evidence is in the trail itself. Spectroscopy shows these are not stars it has stolen or collected, but stars it is actively forging. The leading theory is as dramatic as the observation. Astronomers believe this black hole was once at the center of a galaxy that merged with another. When the two galaxies combined, so did their central supermassive black holes. As these monstrous objects spiraled together and finally merged, the event was so asymmetrical that it sent a powerful gravitational wave recoil, a literal kick in one direction. This kick was so immense it ejected the newly formed, single black hole from the heart of its galaxy entirely. Now, as it plows through the thin gas of intergalactic space at incredible speed, that gas is being compressed, shocked, and funneled along behind it. Under the right conditions, this compressed gas cools and collapses, igniting into chains of young, blue stars. The implications are profound. We have long thought of supermassive black holes as the anchors of their galaxies, unmoving monarchs sitting on thrones of stars. This discovery shows they can be evicted, turned into cosmic nomads. It provides the first real observational evidence for the chaotic aftermath of black hole mergers and the powerful recoils predicted by Einstein's theory. Furthermore, it reveals a new, unexpected method of star formation. Stars are not just born in the peaceful nurseries of galactic disks. They can be sparked in the turbulent, high-speed wake of a runaway monster. This single image forces us to rewrite the life story of galaxies. Their central engines are not always permanent fixtures. Sometimes they are shot out into the dark, leaving behind a trail of new light as their only lasting signature. That runaway black hole shows how even the most extreme objects can create the conditions for new beginnings. But what if we have been looking for life in all the wrong places, and the most promising clue was hiding next door? The story of phosphine on Venus is a masterclass in how modern science wrestles with its own most thrilling possibilities. It began with an announcement that sent shockwaves through the scientific community and the public imagination. A team of astronomers reported detecting the spectral signature of phosphine gas in the temperate cloud decks of Venus. On Earth, phosphine is a molecule almost exclusively associated with life. It is produced by microbes in oxygen-free environments like swamps or industrially in labs. Finding it in significant quantities on a rocky planet was immediately flagged as a potential biosignature, a hint that microbial life could be floating in the sulfuric acid clouds of our neighboring world. The initial excitement was electric, a narrative of finding life just a stone's throw away in cosmic terms. But science at its best is a process of relentless scrutiny. Other teams rushed to reanalyze the same data, and the debate grew intense. The central question was whether the signal was truly phosphine, or if it could be explained by something else. Some argued the data processing might have inadvertently created the phosphine signal from background noise. Others suggested more exotic geological or chemical processes unknown to us could produce the molecule on a hellish world like Venus. The initial team stood by their analysis, but the certainty began to fracture under the weight of collective examination. This is not a failure of science, but its essential engine. Every extraordinary claim must survive an extraordinary gauntlet of verification. More recent studies using different telescopes and refined methods have complicated the picture further. Some have failed to detect phosphine at all, while others have detected only trace amounts far lower than the initial report. The current scientific consensus leans heavily toward skepticism. The phosphine signal, if it exists, is now thought to be much fainter and its origin far more likely to be from non-biological chemistry we do not yet fully understand. The thrilling biosignature hypothesis has receded, but it has not vanished. It remains a tantalizing, unresolved question mark hanging in the Venusian haze. This entire episode clarifies something profound about our search for life. It is not a straightforward treasure hunt, but a painstaking exercise in eliminating all other possibilities. Venus, with its crushing surface pressure and scorching temperatures, is a reminder that habitability is a delicate balance. Its clouds, however, represent a niche, a pocket of relative mildness in an otherwise hostile world. The phosphine story, from its dramatic announcement to its contentious unraveling, shows us that the journey is as important as the destination. It forced us to look at our sister planet with new eyes, to question our assumptions about where life could persist, and to develop sharper tools for the next inevitable discovery. The search continues, not with diminished hope, but with a hardened resolve to be certain. For if we ever do find incontrovertible proof of life elsewhere, we must be absolutely sure we are not just seeing a reflection of our own desperate hope in the data. The search for life demands we question our most basic assumptions, and nowhere is that more true than with the invisible scaffolding of the cosmos itself. Our sixth discovery is a galaxy that seems to defy the universe's own rules, a place where the dominant force of our reality appears to be missing. The galaxy is called NGC 1277, a massive lenticular system relatively close by in cosmic terms. For decades, the standard model of cosmology has rested on a foundational pillar, dark matter. This mysterious, invisible substance does not emit or reflect light, but its gravitational pull is the cosmic glue holding galaxies together. Without a vast halo of dark matter enveloping them, the stars in a fast-spinning galaxy should simply fly apart, like children flung from a merry-go-round spinning too quickly. Yet when astronomers measured the velocities of stars within NGC 1277, they found something astonishing. The stars were moving at speeds that could be entirely explained by the gravity of the visible matter alone, the stars and gas we can see. There was no need for and no sign of a dark matter halo. This is not the first time such a claim has been made. Several years ago, a galaxy called DF2 made similar headlines, though later analyses suggested its distance, and therefore its mass calculations might have been off. NGC 1277 reignites the debate with fresh, high-precision data. The implications are seismic. If confirmed, a galaxy without dark matter is a direct challenge to our understanding of how galaxies form. The prevailing theory says galaxies are born within cradles of dark matter, which draws in gas to form stars. A galaxy lacking this dark matter scaffold would be like finding a skyscraper built without a steel frame, seemingly defying the laws of physics. So what could explain it? Astronomers are wrestling with two broad interpretations. The first and most conservative is measurement error. Perhaps the geometry of the galaxy or the complex motions of its stars are tricking our instruments, making it appear as if dark matter is absent when it is actually present in a hard-to-detect configuration. The second interpretation is far more thrilling. It suggests NGC 1277 may be a relic, a pristine survivor from the very early universe. One theory proposes it formed during a period of rapid, turbulent gas collapse before dark matter halos had fully developed. Another, even more dramatic idea is that it lost its dark matter in a violent gravitational encounter, stripped away by a close pass with another massive galaxy. Each possibility opens a new window. If it is a primordial relic, it offers us a direct look at a rare and ancient mode of galaxy formation. If it was stripped, it reveals the violent gravitational dynamics that can reshape galaxies on a fundamental level. This is not merely an academic debate. It forces us to ask whether dark matter is an inseparable component of every galaxy, or just a common ingredient in a more diverse cosmic recipe. The mystery of NGC 1277 holds up a mirror to our theories, and for now, those theories are staring back, unsettled and unsure. But the question of what lies beyond our solar system is not always a matter of distant telescopes. Sometimes the evidence comes to us. On January 8, 2014, a brilliant fireball streaked across the pre-dawn sky north of Papua New Guinea. It was a meteor, a space rock burning up in Earth's atmosphere, an event so common that observatories log hundreds each year. This one, catalogued as CNEOS 2014-01-08, was different. For years, its data sat in a public NASA database, just another entry. Then, a pair of Harvard astrophysicists took a closer look. They meticulously analyzed the object's recorded velocity and, crucially, its trajectory through the solar system. The numbers told a story that was impossible to ignore. This rock was moving far too fast. Its path was not a lazy orbit around our sun, like every other asteroid or comet we track. Its speed and angle indicated it was a visitor from another star system, traveling on a hyperbolic orbit that meant it was just passing through. In 2019, after rigorous peer review, the scientific community formally confirmed it. CNEOS 2014-01-08 became the first known interstellar meteor to strike our planet. Think about that for a moment. A fragment of another star system, perhaps a piece of a distant exoplanet or debris from its formation, had been drifting in the void for millions or even billions of years. Its journey ended in a flash of light over the Pacific Ocean, delivering the first physical sample of interstellar material we have ever knowingly encountered. The scientific value of such a sample is incalculable. It is a time capsule and a Rosetta Stone from another cosmic neighborhood. To study its composition would be to read the chemical recipe of a place we may never directly visit. Driven by this potential, a scientific expedition was launched. A team meticulously calculated the meteor's likely impact zone based on the military sensor data that had tracked its final moments. They chartered a ship, sailed to the remote location, and used a magnetic sled to scour the ocean floor. The search was for tiny spherules, microscopic beads of molten rock that would have formed as the object vaporized. The expedition reported recovering hundreds of these tiny metallic spheres with a composition unlike any known solar system alloys. While the interstellar origin of these specific spherules remains an active topic of scientific debate and requires further verification, the very attempt highlights a paradigm shift. We are no longer passive observers of the interstellar medium. We have proof that pieces of it can and do land on our doorstep. The confirmation of that 2014 fireball transforms our perspective. The boundary between our solar system and the galaxy beyond is not a wall. It is a sieve with material flowing in both directions. It raises a thrilling possibility. What other interstellar visitors have we missed, and what secrets about the building blocks of other worlds are already lying hidden in the deep ocean sediments or even in our own backyards? The idea that pieces of other star systems are landing on Earth is humbling, but it pales next to a discovery that suggests entire worlds can be born in isolation. The James Webb Space Telescope, peering into the iconic Orion Nebula, has found something that should not exist according to our textbooks. They are not planets and they are not stars. Astronomers call them JWMBOS, short for Jupiter Mass Binary Objects. The name itself is a confession of bewilderment. These are objects roughly the size of Jupiter, but they are not orbiting a star. Instead, they drift freely through the nebula, untethered to any solar system. Even more bizarrely, many of them are found in pairs, two Jupiter-sized worlds locked in a gentle dance around each other, a miniature binary system with no sun at the center. This discovery has sent planetary formation theories into a state of profound confusion. We have two main models for how planets come to be. The first is core accretion, where dust and gas in a disk around a young star slowly clump together over millions of years to build planets. The second is gravitational instability, where a portion of that disk rapidly collapses under its own gravity. Both processes, however, require a star. A star provides the disk of raw material and the gravitational anchor. JWMBOS have no star, they are orphans from birth. So how did they form? One possibility is that they formed like stars do, from the direct collapse of a small, dense knot of gas in the nebula. But Jupiter's mass is incredibly low for such a process, at the very bottom edge of what we thought was possible for star formation. It would be like trying to start a campfire with a single, damp matchstick. Another, more dramatic theory is that these objects were born around stars in the crowded stellar nursery of the Orion Nebula, but were violently ejected by gravitational interactions flung out into the void. Yet this explanation struggles with the pairs. Gravitational ejections are chaotic and violent. For two objects to be thrown out together and remain gravitationally bound to each other is like two people being thrown from a speeding car and managing to hold hands all the way to the ground. It is possible but astronomically unlikely, and yet Webb found many such pairs. This suggests a third, even more radical idea. Perhaps there is an entirely unknown pathway for planetary mass objects to form, a process that works in the cold, dark stretches of space between the stars. JWMBOS are not just a new class of object, they are a direct challenge. They tell us that the universe is more creative and more prolific at making isolated worlds than we ever dreamed. If free-floating, paired planets are common, it forces us to rewrite the opening chapters of every astronomy textbook. The cosmos may be filled with countless such nomadic worlds, dark and alone, or paired in eternal orbits, forming a hidden population that has, until now, remained completely invisible to us. The nomadic JWMBO worlds hint at formation processes we do not yet understand, but to find a star that breaks the rules, we must look back to the very beginning. In the distant halo of our Milky Way, astronomers have identified a star with a chemical fingerprint that should be impossible. It is called SMSS J2003-1142, a faint point of light that is a true relic from the cosmic dawn. Its composition is staggeringly primitive. The star contains almost no metals, a term astronomers use for any element heavier than hydrogen or helium. This extreme purity marks it as a member of the legendary second generation of stars, born from the ashes of the very first ones to ignite after the Big Bang. Those first stars, known as Population 3, were behemoths made of pure hydrogen and helium. They lived fast, died young, and in their violent supernova deaths, they forged the first heavy elements and seeded them into the cosmos. The next generation of stars, like SMSS J2003-1142, formed from this newly enriched gas. Their chemical makeup is therefore a direct record of those first supernova explosions, a fossilized snapshot of the universe's earliest chemistry. And this is where the mystery deepens. While this star has the expected incredibly low levels of common metals like iron, it shows a surprising and significant abundance of much heavier elements, including uranium. This is a profound contradiction. The models for those first supernovas suggest they could produce some heavier elements, but not in the specific pattern we see here. The amounts of uranium and similar elements are too high, and their ratio to lighter elements is all wrong. It is like finding an ancient clay tablet that should only contain simple pictograms, but instead has a complex mathematical equation etched into it. The star is telling us that the very first stellar deaths were far more varied and powerful than we thought. Perhaps some of those primordial giants died in a rare type of supernova that was exceptionally efficient at forging heavy elements, a colossal explosion unlike anything commonly seen in the modern universe. Or the environment around this star's birth was seeded by the merger of two neutron stars, an event now known to be a primary cosmic forge for gold, platinum, and uranium, but one thought to be exceedingly rare in those early epochs. This single ancient star forces a rewrite of the opening chapters of cosmic chemical evolution. It tells us the first steps in building the elements for planets and life were not a slow, uniform process, but a chaotic and explosive drama, with events capable of creating surprising chemical pockets in the infant cosmos. We are not just looking at an old star, we are reading a surviving page from the universe's own recipe book, and it contains instructions we are only beginning to decipher. The ancient chemistry of those first stars laid the foundations for everything to come, but the universe was already weaving those ingredients into structures of unimaginable grandeur. Far across the cosmos, at a distance so vast its light has been traveling for over 12 billion years, astronomers have mapped a structure that defies easy description. They call it the cosmic vine. Imagine the largest root system of an ancient, sprawling tree, but one woven from galaxies instead of wood. This is not a cluster or a loose group, but a thin, filamentary megastructure, a thread in the tapestry of the cosmic web caught at a moment of dramatic assembly. The scale is almost paralyzing. The cosmic vine stretches for nearly 13 million light-years in length, yet it is only about 650,000 light-years thick. It is a river of galaxies flowing through the void, with dozens of massive galaxies strung along its spine like luminous beads. We are seeing it as it was when the universe was only a quarter of its current age, a direct snapshot of the universe's skeleton during its most vigorous period of growth. Its significance lies in this pristine timing. The cosmic web, the vast network of filaments and voids that structures the universe, is predicted by our models of dark matter and gravity. We see its mature form in the relatively nearby universe, a settled architecture. But catching a filament like the cosmic vine so early is like finding a photograph of a skyscraper while its steel frame was still being welded together. It allows us to test our theories of cosmic evolution in real time, or rather, in deep time. How quickly do galaxies flow into these filaments? How do they ignite with star formation as they are funneled together? the vine shows us that even at this early epoch, the universe's matter had already collapsed into these vast linear highways, channeling galaxies toward the dense nodes where future galaxy clusters would form. One of the most startling details is the presence of two massive, quiescent galaxies at its heart, galaxies that had already stopped forming stars in a universe that was still in its wild, star-making youth. This suggests that the densest environments within these early filaments could accelerate a galaxy's life cycle, rushing it from vibrant birth to quiet maturity at a pace we did not anticipate. The cosmic vine is more than a record, it is a laboratory. By studying its dimensions, the motions of its galaxies, and the types of stars they contain, astronomers can run the clock forward and backward, checking if our simulations of cosmic growth match this spectacular relic. It confirms that the universe builds from the bottom up, starting with these delicate threads before knitting them into the great walls and clusters we see today. Each filament like this is a backbone of creation, and for the first time we are watching the vertebrae form. The cosmic web provides the universe's grand architecture, but its most intricate machinery is found in the dizzying spin of a stellar corpse. In the constellation Sextans, a cosmic lighthouse is behaving in a way that defies all expectations. The pulsar known as PSR J1023+0038 has a simple, brutal history. It is the crushed core of a massive star that exploded, leaving behind a city-sized sphere of pure neutron star material spinning hundreds of times every second. Like all pulsars, it beams radiation from its magnetic poles, and if those beams sweep past Earth, we see a regular pulse, a metronome of the cosmos. This particular pulsar, however, has a companion, a normal star locked in a tight orbital dance. And every few years, without warning, the pulsar undergoes a dramatic identity crisis. It abruptly switches between two completely different states. For a period, it shines brightly in X-rays, a powerful source of high-energy radiation. Then, just as suddenly, it dims in X-rays and instead begins pulsing brilliant beams of radio waves, the classic signature of a pulsar. It is as if a lighthouse keeper were randomly swapping between a blinding spotlight and a steady, rhythmic beacon. This bizarre switching, observed with space-based X-ray telescopes and ground-based radio arrays, has provided astrophysicists with a unique natural laboratory. The leading explanation involves a delicate and violent balance of forces, a model called the propeller mechanism. The pulsar's companion star is so close that its outer atmosphere is constantly being pulled away by the pulsar's immense gravity. This stream of gas flows toward the pulsar, forming a swirling disk of superheated plasma around it. In its radio-bright state, the pulsar's powerful magnetic field and rapid spin act like a fierce cosmic wind, pushing this accretion disk away, preventing the gas from reaching the surface. The pulsar's own rotation powers its radio beams unimpeded, but sometimes the balance tips. The flow of gas from the companion star may increase just enough to overwhelm the magnetic barrier. The inner edge of the disk pushes inward, and when it crosses a critical boundary, the pulsar's magnetic field suddenly grabs hold of it. Now, instead of being flung away, the gas is channeled along magnetic field lines at nearly the speed of light, slamming into the pulsar's magnetic poles. The impact heats the gas to temperatures of millions of degrees, creating two searing hotspots that erupt in X-rays. In this state, the pulsar is actively feeding, and the process somehow quenches its regular radio emission. Then, just as mysteriously, the accretion flow weakens, the magnetic field regains the upper hand, and the system flips back to its radio pulsar state, pushing the gas away once more. This back-and-forth struggle, this cosmic tug-of-war between gravity and magnetism, is what we witness as the sudden switch in emission. Studying this system gives us an unprecedented view of plasma physics under the most extreme conditions imaginable. We can watch how matter behaves when torn apart by gravity and accelerated by magnetic forces we can never replicate on Earth. Each switch is a data point, a clue to understanding how all pulsars with companions interact with their environment, and perhaps how the most powerful magnets in the universe are born and die. The violent physics of a pulsar's magnetic struggle is a spectacle of cosmic forces, yet a gentler but no less dramatic evaporation is reshaping worlds in other star systems. Astronomers have found a planet that is quite literally blowing away in the stellar wind. The world is WSP-69b, a gas giant orbiting perilously close to its sun, completing a full year in less than 4 Earth days. This proximity subjects it to a blistering torrent of radiation and charged particles, and the planet is responding in a spectacular fashion. It has developed a giant comet-like tail. Observations using specialized instruments on ground-based telescopes have captured the telltale signature of helium gas streaming from the planet's atmosphere and being swept back by the pressure from its star, forming a vast trailing plume that stretches for at least 350,000 miles into space. That is a tail longer than the distance from Earth to the Moon. Detecting this required a clever technique. When the planet transits, passing in front of its star, astronomers don't just look for the dip in the star's overall brightness. They use a spectrograph to break the starlight into a rainbow of colors and look for a specific, subtle absorption line caused by helium. As the planet and its extended atmosphere move across the star's face, this helium signature appears not just during the main transit, but also slightly before and after, revealing the enormous cloud of gas being stripped away. This is not a gentle leak, but a continuous, catastrophic loss. The planet's outer atmosphere is being heated to such extreme temperatures that the gas expands beyond the gravitational pull of the planet itself. The star's relentless radiation and wind then catch this bloated envelope and sweep it into space like steam billowing from a boiling kettle caught in a strong breeze. For WSP-69b, this process is a preview of its ultimate fate. Over hundreds of millions of years, this relentless stripping could potentially evaporate the entire gaseous envelope, leaving behind only a barren, rocky core, a ghost of a giant. This discovery transforms our understanding of planetary evolution. We once thought of gas giants as stable, permanent fixtures once formed. Now we see they can be dynamic and transient, especially in the intense neighborhoods close to their stars. By studying the rate of this atmospheric escape, astronomers can calculate the life expectancy of such worlds. More profoundly, it gives us a new lens through which to view our own solar system's history. Did any of our gas giants undergo a similar violent phase in their youth? Could some of the strange super-Earth exoplanets we find be the leftover cores of evaporated hot Jupiters? WSP-69b, with its magnificent doomed tail, is a real-time demonstration of a planet's atmosphere unraveling, a vivid reminder that even the largest worlds are not immune to the ravages of their sun. The heart of our own galaxy is a place of unimaginable density and violence, yet its deepest mysteries arrive not with a roar but in a series of enigmatic whispers. Near the Milky Way's core, astronomers have detected strange radio sources that flare to life with startling brightness, only to vanish back into silence for years at a time. One of the most famous is known as GCRT J1745-3009. This object and others like it defy all our existing labels. They are not the steady ticks of pulsars or the furious outbursts of magnetars. Instead, they erupt in powerful, minutes-long bursts of radio waves repeating at intervals that seem utterly unpredictable. Imagine a distant lighthouse that flashes with blinding intensity once every few years, but you can never guess which night it will choose to illuminate. For over a decade, these Galactic Center radio transients have remained a profound puzzle. Their brief, brilliant appearances give scientists just enough data to be intrigued, but never enough to solve them. The signals are too long to be from a pulsar, which emits millisecond pulses, and too short and infrequent to be from any known type of flaring star. The leading theories stretch our understanding of stellar end states. One possibility is that these are a new type of stellar remnant, perhaps an ultra-long period magnetar, a highly magnetized neutron star that builds up energy over years before releasing it in a single radio-bright burst. Another idea involves a binary system where a compact object, like a white dwarf or neutron star, orbits through the diffuse atmosphere of a companion star. Each pass could trigger a shock wave in the surrounding gas, lighting it up like a match struck in the dark. The sheer unpredictability is what makes them so maddening and so compelling. Astronomers must monitor the chaotic Galactic Center constantly, hoping to catch one of these phantoms in the act to get a second or third look that might reveal a pattern. Their existence suggests an entire population of faint, intermittent objects we have barely begun to catalogue, objects that spend most of their lives in hibernation, only occasionally announcing their presence to a universe that is rarely paying attention. These radio whispers from the core remind us that even in our own cosmic backyard, new classes of celestial phenomena are still waiting to be defined, their brief flares like coded messages from the dark. While the Galactic Center sends out cryptic radio whispers, it can also act as a cosmic catapult, launching stars into the eternal dark. The evidence for this is a sun named S5HVS1, a solitary traveler racing through the Milky Way's halo at a staggering 1,700 kilometers per second. At that speed, a journey from Earth to the Moon would take a mere 6 minutes. This is no ordinary star drifting with the galactic current. It is a runaway, a hypervelocity projectile flung from the very heart of our galaxy. By meticulously tracing its path backward across millions of years, astronomers have pinpointed the origin of its incredible speed, a single, terrifyingly close encounter with Sagittarius, a star, the supermassive black hole at the Milky Way's core. The mechanism is a classic, if extreme, demonstration of celestial mechanics known as the Hill's mechanism. Imagine a binary star system, two suns orbiting each other, wandering too close to the black hole's immense gravitational well. The tidal forces can tear the pair apart. One star is captured into a tight orbit around the black hole, while the other is violently slingshotted outward, gaining a tremendous burst of velocity like a stone from a sling. S5HVS1 is that flung stone. Its trajectory is a near-perfect line pointing directly back to Sagittarius, a star, a cosmic crime scene with a single, obvious suspect. But this star is more than just a velocity record holder. Its composition tells a deeper story about its birthplace. Detailed spectroscopy reveals it is a type main sequence star, a relatively common hot and blue-white sun. Crucially, its chemical signature is a perfect match for the stars found in the Galactic Center, the crowded stellar nursery that surrounds the black hole. This forensic evidence confirms it is a native of the core, not an intruder from another galaxy or a wandering visitor. By studying its light, we are essentially reading the DNA of a star that was born in the most chaotic neighborhood imaginable and then violently evicted. This observation provides the clearest, most direct proof of the black hole's power to reshape its surroundings through gravitational interactions. It transforms Sagittarius, a star, from a passive monster at the center of a slow orbital dance into an active sculptor, capable of hurling entire stars into the galactic wilderness. The existence of S5HVS1 implies there may be many more such hypervelocity stars already departed, streaming silently through the dark halo, each one a testament to a moment of supreme violence at the galaxy's heart. They become celestial fossils, their paths and speeds encoding the history of gravitational encounters we can no longer directly see. That hypervelocity star is a testament to the black hole's power to eject, but what about the black holes that stayed behind, growing to impossible sizes? The James Webb Space Telescope has peered back to when the universe was a mere 570 million years old and found a paradox. In a small, faint galaxy catalogued as CEERS 1019, it discovered a supermassive black hole of staggering proportions. The galaxy itself is modest, a compact collection of young stars. The black hole at its heart, however, is not. It weighs in at around 10 million solar masses. To put that in perspective, the supermassive black hole at the center of our own mature Milky Way, Sagittarius A star, is about 4 million solar masses. This ancient black hole, observed in the universe's infancy, is already more than twice as heavy as our local giant, yet its host galaxy is hundreds of times smaller than the Milky Way. This discovery creates a profound tension in our understanding. According to the standard models of cosmic evolution, black holes and their host galaxies grow in tandem over billions of years through a careful dance of mergers and accretion. A galaxy's mass and the mass of its central black hole are usually correlated. CEERS 1019 shatters that correlation for the early universe. Its black hole is overmassive, a giant in a dollhouse. The immediate question is how? How could a black hole accumulate so much material so quickly in such a small galactic environment in less than 600 million years after the Big Bang? The leading theories point to a radically different birth for these primordial monsters. Perhaps the first supermassive black holes did not start as the collapsed cores of massive stars, which would then need to grow for eons. Instead, they may have formed directly from the collapse of immense clouds of primordial gas, skipping the stellar stage entirely and being born as heavy seeds, tens of thousands of times the mass of our Sun. These seeds would then have a colossal head start, feasting on the dense gas of the early cosmos to balloon to supermassive sizes while their host galaxies were still taking their first tentative steps. Another possibility is that the early feeding process was extraordinarily efficient, with gas funneling into the black hole at nearly the maximum theoretical rate, a sustained cosmic feast with very little wasted energy. Or the galaxy itself may have been much larger in the past and was stripped of its outer stars by violent interactions, leaving behind the dense core and its overgrown black hole as a relic of a more massive system. Each explanation challenges our timeline. The existence of such a massive black hole so early forces us to compress the epoch of initial growth, to imagine a universe where the most extreme objects formed in a frantic rush, almost immediately after the first stars flickered to life. CEERS 1019 is not an anomaly, it is a clue. It suggests that the early universe was a place of accelerated, violent physics, where the rules of growth we see in the modern, more sedate cosmos did not fully apply. Every overmassive black hole Webb finds is a stopwatch, telling us just how fast the universe could build its most terrifying structures. The death of those primordial giants was a cataclysm that forged the elements for all future worlds, and we may have just found its ghostly echo. In the distant galaxy known as GN-Z11, the James Webb Space Telescope has detected a chemical fingerprint unlike any other. This galaxy is itself a record holder, one of the most distant and earliest we have ever observed, its light traveling for over 13 billion years to reach us. Within its ancient glow, Webb's instruments picked up an unusual abundance of nitrogen, alongside other elements like carbon and oxygen, but with a striking absence of iron. This specific pattern is the smoking gun, a signature that points theorists toward one of the most violent events the universe can produce, a pair instability supernova from a first-generation star. To understand why this is so monumental, we must revisit the nature of those first stars. Population 3 stars were behemoths composed purely of hydrogen and helium, with masses hundreds of times that of our Sun. Their internal furnaces burned at unimaginable temperatures and pressures. In such an environment, a unique and self-destructive process can occur. The core becomes so hot that light itself, in the form of gamma rays, begins to spontaneously create pairs of electrons and their antimatter counterparts, positrons. This conversion of radiation into particles removes the outward radiation pressure that was supporting the star against its own immense gravity. The core catastrophically collapses, triggering a runaway thermonuclear explosion of such ferocity that it does not just blow off the star's outer layers, it completely obliterates the entire star, leaving behind no black hole, no neutron star, nothing but an expanding cloud of newly forged elements scattered into the void. The chemical signature Webb saw in GN-Z11 matches the predicted fallout from just such an event. The high nitrogen suggests the explosion processed material in a very specific way, while the lack of iron indicates the star was so massive and its explosion so complete that it did not live long enough to forge the heaviest elements in its core. This is not just another supernova remnant, it is potentially our first direct evidence for the specific death cry of a population 3-star. For cosmology, this is a landmark akin to finding the fossil of a legendary creature we thought had left no trace. It confirms a key chapter in the story of cosmic chemical enrichment, showing that these first stars did not just fade away, they died in titanic explosions that seeded the early cosmos with the raw ingredients for everything that followed. The nitrogen and carbon we see in that ancient galaxy are the direct descendants of that single star-ending event. It transforms our understanding of the early universe from a theoretical sketch into a narrative with physical evidence. We are no longer just simulating those first explosions, we are seeing their aftermath, reading the chemical legacy they imprinted on one of the universe's first galaxies. This detection opens a new window into the era of the first stars, suggesting that by searching for these unique chemical signatures in other ancient galaxies, we can begin to take a census of how those primordial giants lived and died, building a true history of the cosmic dawn from the ashes they left behind. The chemical legacy of those first stars built the ingredients for worlds of every kind, including one that captivated our imagination for years with a story of almost mythical wealth. The super-Earth exoplanet 55 Cancri E orbits a sun-like star just 40 light-years away, so close and so bright that it has become a premier laboratory for atmospheric science. For over a decade, its story was a tantalizing one. Based on its density and the carbon-rich chemistry of its host star, astronomers theorized it could be a carbon planet, its interior so pressurized that much of its carbon had crystallized into a layer of diamond. The idea of a diamond planet, a world literally made of precious gemstone, was a narrative that captured the public mind, a glittering symbol of cosmic extravagance. Then the James Webb Space Telescope turned its gaze toward it, and the story transformed. Webb's exquisite instruments did not detect the spectral signature of a bare, sparkling surface. Instead, they captured the subtle fingerprints of an atmosphere, a shroud of gas enveloping the world. The data suggests this atmosphere is not thin or primordial, but likely secondary, replenished by outgassing from a volatile, rich interior. The most intriguing hints point to the possible presence of carbon dioxide or even methane. This changes everything. A thick, volatile atmosphere implies a planet with a complex geologic life, one that is actively recycling material between its interior and its sky. It complicates the simple, beautiful diamond narrative profoundly. A true carbon-dominated world with a diamond interior would likely be geologically inert, unable to produce such a significant, renewing atmosphere. The new data points toward a world that may still be carbon-rich, but one mixed with other volatile elements like oxygen and hydrogen, allowing for a dynamic, evolving environment. It might be a world with a graphite crust over a silicate mantle, or one with exotic forms of rock we have no name for, venting gases that create a hazy, hot shroud. The temperature at its surface, locked in a scorchingly close orbit, is still infernal, likely far too hot for any known life. But the discovery of this atmosphere is a masterclass in the scientific process. It shows how a compelling, elegant story must yield to the complexity of actual data. 55 Cancri E is no longer just a symbol of cosmic riches. It is a real, messy, and fascinating world, teaching us that even the most extreme exoplanets can hold surprises that rewrite their own legends in real time. But the cosmos is not only a place of brilliant light and violent creation. It also holds pockets of profound stillness where the very act of ignition seems to have been forgotten. In a quiet corner of the universe, radio astronomers have mapped a ghost, an object catalogued as J0613+52. What they found was not the blazing disk of a spiral or the fuzzy glow of an elliptical galaxy. Instead, their instruments detected only the faint, diffuse whisper of neutral hydrogen gas, the raw fuel for star formation, spread across a volume of space large enough to host a small galaxy. Yet within this vast reservoir of potential, there were no stars, no clusters, no nebulae, no pinpricks of nuclear fire. This is a dark galaxy, a cosmic silhouette where the lights never came on. Its existence challenges a fundamental assumption that where you find enough gas, gravity will eventually pull it together to spark stars. J0613+52 holds enough hydrogen to birth billions of suns, but for reasons we are only beginning to understand, that process has stalled or never begun. The galaxy appears pristine, a frozen relic of the early universe, having drifted through cosmic time in near-perfect isolation, untouched by the gravitational encounters that stir and compress gas in busier galactic neighborhoods. This profound solitude may be the key to its darkness. Without the shockwaves from supernova or the gravitational nudges from passing galaxies, the gas within may simply be too calm, too diffuse, to collapse into the dense cores required to ignite stars. It is a cosmic still life, a snapshot of potential energy that has never been tapped. Studying this object is like finding a perfectly preserved, unlit furnace, all the fuel neatly stacked beside it. By analyzing the distribution and motion of its gas, astronomers can probe the exact conditions that prevent star formation, testing the thresholds of density and turbulence required to turn a cloud into a sun. This dark galaxy offers a unique control experiment, showing us what the universe looks like when one of its most basic processes is paused. It raises a haunting possibility that scattered throughout the voids are countless such dark halos, invisible islands of untouched gas that have existed since the beginning, silent and unchanging, representing a road not taken in the story of cosmic evolution. The stillness of a dark galaxy is one extreme, but the heart of a stellar corpse can generate a different kind of quiet, one of focused, terrifying power. Swift J18.0-1607 is a neutron star discovered in 2020, and it refuses to fit neatly into our cosmic filing system. This city-sized ball of ultra-dense matter spins rapidly, completing a rotation every 1.36 seconds, which initially marked it as a fairly standard, if young, pulsar. But its magnetic field tells a different story. Measurements reveal a magnetic strength that is staggeringly powerful, yet curiously sits in a no-man's land between two established classes of objects. It is about 1,000 times more magnetic than a typical pulsar, but also about 1,000 times weaker than the most extreme magnets in the universe, the magnetars. This places it squarely in an elusive intermediate zone, a rare breed that challenges our simple binary classification. For decades, astronomers have categorized highly magnetized neutron stars as either one thing or the other. Magnetars possess magnetic fields so intense they can literally crack the star's solid crust, powering enormous starquakes and bursts of high-energy radiation. Regular pulsars have strong but more manageable fields that power their steady, lighthouse-like beams. Swift J18.0-1607 blurs this line, behaving at times like a pulsar with its steady radio pulses, while also showing the X-ray variability and outbursts more characteristic of a magnetar. This hybrid nature makes it a crucial missing link, a living laboratory for understanding magnetic life cycles. One leading theory suggests that all neutron stars are born with incredibly strong magnetic fields, but for most, this field decays rapidly within the first few tens of thousands of years. What we call a magnetar, then, might simply be a neutron star whose ultra-strong field has, by chance or circumstance, not yet decayed. A star like Swift J1818.0-1607 could be caught in the act of this transformation, its field strength waning from a magnetar level down toward that of a normal pulsar. By studying its precise behavior, the rate of its spin slowdown, and the energy of its occasional outbursts, scientists can map this evolutionary pathway in real time. It helps answer fundamental questions. Do magnetars eventually become quiet, ordinary pulsars after their magnetic fury fades, or are they a distinct population destined for a different end? Each observation of this intermediate object refines our taxonomy, forcing us to see neutron stars not as static types, but as characters in a dynamic story of magnetic decay and stellar aging. In its ambiguous signal, we find the key to understanding how the universe manages its most concentrated reservoirs of magnetic energy, and how even in death, a star's story is one of constant, slow change. The magnetic life of a neutron star unfolds over millennia, but the oldest story of all is written in the faint, cold glow that fills every direction. This is the cosmic microwave background, the afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. For the most part, this primordial light is remarkably uniform, a tapestry of tiny temperature fluctuations that seeded all future structure. But one feature stands out as a profound anomaly, a region so large and so cold it has troubled cosmologists for nearly 2 decades. They call it the Great Cold Spot. Stretching across a vast swath of the southern sky, this region is significantly cooler than the surrounding background by about 70 microkelvins. While that sounds minuscule, its sheer size makes it statistically extraordinary. The chance of such a large, cold feature appearing randomly in our standard model of the cosmos is less than 2%. For years, the leading explanation was that it might be a cosmic mirage, a giant supervoid, an immense, mostly empty region of space lying between us and the CMB. The light from the background passing through such a void would lose energy, creating a cold spot in our maps. Yet, when astronomers went looking for this proposed supervoid, they found nothing large enough or empty enough to explain the effect. The void hypothesis began to crumble. This left a far more exotic possibility on the table, one that reaches back to the universe's first moments. The cold spot could be the imprint of a cosmic texture. Imagine the fabric of spacetime in the infant universe undergoing a phase transition, like water freezing into ice. In that process, defects can form knots or twists in the very structure of reality. A cosmic texture is one such topological defect, a tangled region of energy density frozen into the cosmos. If one existed within our horizon at the time the CMB was emitted, its gravitational influence would have left a distinct circular cold signature, exactly the kind we see. New, sophisticated simulations of the early universe now allow scientists to test this idea with unprecedented precision. They can model the formation and evolution of textures and compare their predicted imprints to the actual cold spot data. The results are tantalizing but not yet conclusive. Some analyses show the cold spot's profile and sharp edges are more consistent with a texture than with a random statistical fluctuation. Others argue that more complex analyses of the full CMB data still allow for the possibility, however slim, that it is just a rare fluke in an otherwise standard cosmos. The debate is a beautiful example of science at the frontier. On one side, the elegant, minimal explanation of a simple statistical anomaly. On the other, the thrilling prospect of evidence for physics from the first fractions of a second after creation, a fossil from an era of unified forces we can only theorize about. The Great Cold Spot remains an open wound in our cosmological models, a quiet, cold question mark on the oldest map we have. Its resolution, whether as a cosmic defect or a statistical ghost, will tell us if we must rewrite the very first chapter of universal history, or if the universe simply played a trick on us, leaving one last great puzzle in its primordial light. The ancient light of the cosmic microwave background maps a universe of grand scales, but some of the most delicate structures hide in our own celestial backyard. Orbiting between Saturn and Uranus is a small, dark world named Chariklo, classified as a centaur, a hybrid object caught between asteroid and comet. For decades, it was just another faint point of light until a remarkable event in 2013 transformed our understanding of what small bodies can be. Astronomers were watching as Chariklo passed in front of a distant star, an event called a stellar occultation. They expected the star's light to simply wink out as the asteroid blocked it. Instead, the light flickered. It dimmed not once but several times, both just before and just after the main occultation. The pattern was unmistakable, and it was the signature of rings. Two thin, dense rings of icy particles were circling this tiny world, only 250 kilometers across. This made Chariklo the smallest known object in the solar system to possess a ring system, a title once held exclusively by the gas giants. The initial discovery was stunning, but it was just the beginning. Since then, multiple teams have organized campaigns to catch Chariklo in other occultation events. By deploying networks of telescopes across the paths of these shadows, they have turned these chance alignments into a powerful mapping tool. Each new observation adds another slice of data, another cross-section of the rings from a slightly different angle. Over time, this has allowed astronomers to construct an increasingly precise portrait of this miniature Saturn. We now know the rings are remarkably sharp-edged and confined, likely shepherded into their neat bands by the gravitational influence of one or more tiny, unseen moons. The material within them reflects light in a way that suggests it is composed of water ice, possibly mixed with darker organic compounds, making them brilliant but narrow bands of frozen debris. The central mystery, of course, is how such a small body acquired rings in the first place. With such a weak gravitational field, Chariklo could never have captured and held a cloud of passing debris. The leading theory points to a violent and recent event in its past, a collision. The scenario is a dramatic one. Sometime in the last few million years, perhaps even more recently, another small asteroid or comet struck Chariklo. The impact did not shatter the centaur, but it blasted a plume of material into space. Much of that debris would have escaped entirely, but a significant fraction, moving at just the right speed, found itself trapped in orbit. Over time, collisions between these particles and the gentle, persistent forces of gravity would have smoothed this chaotic cloud into the thin, flat disks we see today. The existence of these rings is a testament to the dynamic, cluttered nature of the outer solar system, where such collisions are not rare ancient history but ongoing processes. Chariklo's rings are more than a cosmic curiosity, they are a natural laboratory. By studying how such delicate structures form and persist around a minuscule world, we gain insights into the processes that likely shaped the early solar system, when similar disks of debris swirled around young planets, eventually coalescing into moons. This tiny, dark centaur, with its brilliant hoops of ice, reminds us that complexity and beauty are not the sole domain of planets. Even the smallest wanderers can hold onto their own exquisite, fleeting architecture, a silent record of a single, shattering moment in time. The delicate architecture of Chariklo's rings reveals a solar system still sculpting itself through collisions, but around a dead star, such an impact leaves a very different kind of scar. In the constellation Scorpius, a white dwarf star designated WD 0816-310 presents a ghostly face marked by a single concentrated blemish. This stellar corpse, the dense Earth-sized core of a sun-like star that has shed its outer layers, should have a pristine surface. The intense gravity of a white dwarf is so strong that any heavy elements like iron, calcium, or magnesium should quickly sink into its interior, leaving behind an atmosphere of pure hydrogen or helium. Yet when astronomers analyzed the light from this particular white dwarf, they detected the unmistakable signatures of metals. More astonishingly, these metals were not evenly distributed. As the star rotated, the metallic signals appeared and disappeared in perfect synchronization, revealing a concentrated patch of material fixed to one spot on its surface, like a dark tattoo on a pale sphere. This is the metallic scar, and its origin story is one of cosmic cannibalism. The leading explanation is both elegant and violent. The white dwarf's powerful magnetic field, a relic of its active past, acts as a cosmic funnel. Sometime in the recent past, an asteroid or perhaps a small planetesimal from the star's own surviving planetary system ventured too close. The white dwarf's immense tidal forces shredded the rocky body into a stream of dust and gas. Instead of this debris raining down evenly across the star, the magnetic field captured and channeled the ionized material, directing it directly to the magnetic north and south poles, where it accumulated into a dense metallic scar. This observation is monumental because it provides the most direct evidence yet of the final fate of many planetary systems. We are watching in real time the consumption of planetary building blocks by the star they once orbited. It confirms a long-standing theory about the polluted atmospheres of many white dwarfs, suggesting that the metals we detect are not from the star itself, but from the rocky debris of its own children devoured after its death. This scar is more than a curiosity, it is a forensic report. By analyzing the specific metals in that concentrated patch, astronomers can perform an autopsy on the destroyed object, determining its composition, its size, and even its history. Was it a dry, metallic asteroid, a water-rich protoplanet? Each element tells a part of the story. This process reveals the ultimate recycling of a solar system, where the raw materials of planets are returned to the stellar forge, perhaps to one day be part of something new in the cosmic cycle of birth and death. The magnetic scars of a white dwarf are a local drama, but the most powerful signals in the universe arrive from across cosmic gulfs with a single, brilliant millisecond flash. Fast radio bursts, or FRBs, are among the most energetic and mysterious events we detect, releasing as much energy in 1,000th of a second as our Sun does in 3 days. Most appear once and vanish, making them impossible to pin down. But a few precious sources repeat, and one in particular has led us to a deeply unexpected home. Using a global network of radio telescopes, astronomers have pinpointed a repeating FRB to a very specific and surprising location within a distant galaxy. It is not embedded in a region of frantic star formation, where young, massive neutron stars are commonly found. Instead, the signal originates from a globular cluster, a dense, spherical swarm of ancient stars that orbits the galaxy like a distant, fossilized satellite. This environment is a cosmic retirement home, filled with stars that are billions of years old. It is the last place anyone expected to find the source of such a violent, youthful eruption. The leading suspects for most FRBs have been magnetars, incredibly magnetic young neutron stars born from the explosive deaths of massive stars. But massive stars live fast and die young. They do not exist in these ancient stellar communities. So what is creating these brilliant flashes in a place where the stellar population is geriatric? The answer may lie in a slower, more patient path to creating a magnetar. Theorists are now exploring a fascinating possibility that the source could be an ancient magnetar formed through the merger of two white dwarfs. In this scenario, two dead stellar cores in a tight binary orbit would slowly spiral together over eons. When they finally merge, the colossal energy of their collision could forge a new object, a neutron star with an immensely powerful magnetic field. a magnetar born not from a quick supernova, but from a slow gravitational dance. This resurrected stellar corpse, suddenly imbued with magnetic fury, could then produce the intense bursts of radio waves we see. Alternatively, the source could be an ultra-long period pulsar, or even a highly magnetized white dwarf itself, objects that could naturally persist in an old stellar population. The localization of this FRB to a globular cluster is a crucial clue that forces a major rethink. It tells us that the conditions to produce these cosmic lightning strikes are not exclusive to the stellar nurseries of the young universe. They can also arise in the quiet, ancient corners through evolutionary pathways we are only beginning to map. Every time this distant source repeats, it flashes from a realm of ancient stars, challenging our assumptions and proving that the universe keeps its most volatile potential in the most serene of settings. The spiral arms of galaxies are majestic, but to find them wrapped around a single, young star is to witness a solar system's blueprint in the act of being drawn. The James Webb Space Telescope has delivered exactly that, a portrait of cosmic craftsmanship so clear it feels like a diagram come to life. The star is SAO2-06462, a young sun still nestled within its natal cocoon of gas and dust. Webb's infrared gaze pierced through the obscuring haze to reveal the structure of its surrounding protoplanetary disk with breathtaking clarity. And there they were, not a featureless haze, but two distinct, graceful spiral arms sweeping out from the central star like the pattern on a spinning phonograph record. This is not an artist's impression, it is a direct observation of a dynamic nursery. These spirals are the gravitational signatures of infancy, cosmic wake-up calls written in dust. The leading theory is as elegant as the image itself. Within that disk, one or more young, massive protoplanets are already taking shape. As these embryonic worlds orbit their star, their gravity perturbs the surrounding gas and dust, much like a boat moving through water creates ripples. But in a rotating disk, these perturbations don't radiate out as simple rings. They wind up into these beautiful, sweeping spiral density waves. The material in the arms is slightly denser, slightly brighter, tracing the gravitational influence of the unseen builders. Each spiral arm is essentially a traffic jam in the disk, a region where dust and gas pile up, encouraged to collide and stick together by the planet's gravitational nudge. This makes them not just pretty patterns, but active construction zones, factories where the raw materials of worlds are being gathered and assembled. The specific shape and tightness of the spirals around SAO2-06462 allow astronomers to infer properties of the hidden planets, such as their likely mass and orbital distance. It is a form of celestial detective work, using the distortion in the disk to deduce the presence and character of the objects causing it, long before we could ever see them directly. This observation transforms our understanding of planet formation from a theoretical timeline into a visible, ongoing process. We are no longer just looking at before and after pictures, we are watching the during. The spiral arms are a snapshot of gravitational choreography, a moment in the multi-million-year dance where planets sculpt their own birth environment. It confirms that giant planets can form quickly, their influence felt while the disk is still rich and full. Every curve in that luminous spiral is a chapter in the story of a world being born, a direct glimpse into the moment a star's leftover debris begins to organize itself into new spheres, new possibilities, under the silent guidance of gravity. The elegant spirals of a forming solar system show gravity's gentle hand, but its most powerful grip creates voids in our cosmic census. Our map of black holes is curiously incomplete, missing a crucial link in the family tree. We have found plenty of stellar mass black holes, the remnants of dead stars, and we have located the behemoth supermassive black holes that anchor galaxies. But the middle child, the intermediate mass black hole, has proven frustratingly elusive. Recent wide-ranging surveys have highlighted this deficit, particularly in the environments of dwarf galaxies and certain globular clusters where theory suggests they should be lurking. Their absence is not just a minor gap in a catalogue, it is a fundamental puzzle in the story of cosmic growth. How do the small black holes born from stars grow into the monsters that dominate galactic centers? Intermediate mass black holes weighing between 100 and 100,000 solar masses are the proposed missing link, the stepping stones in this evolutionary pathway. Without them, we face a cosmic chicken and egg problem. Did supermassive black holes start as impossibly heavy seeds from the dawn of time, or did they build up gradually, feasting on gas and merging with smaller black holes over billions of years? If the latter is true, we should see black holes of all sizes along the way, especially in the quiet, less disruptive environments of small galaxies where growth could have proceeded undisturbed. Their apparent scarcity forces a difficult choice. Either our models of how black holes grow through mergers are flawed, or these intermediate objects are hiding in plain sight, masquerading as something else. The hunt is now employing ingenious new strategies. One method listens for the faint, telltale hum of gravitational waves emitted when an intermediate mass black hole devours a smaller stellar mass black hole, a distinct chirp that observatories like LIGO and Virgo are tuned to hear. Another strategy involves scouring the centers of dense star clusters for subtle, collective wobbles in the motions of thousands of stars, a sign of a dark, heavy heart pulling them around. Perhaps the most promising search looks for the flares from tidal disruption events, the brilliant flash when a star is torn apart. The characteristics of that flash, its duration and energy, can reveal the mass of the hidden black hole doing the tearing. Finding these missing giants would do more than fill a blank in a table. It would connect two chapters of cosmic history, showing how the universe builds its most extreme objects from the bottom up. Each candidate, each faint signal, is a potential piece of that bridge, a clue to how gravity assembles its darkest empires from the fragments of dead suns. Buried in the faint starlight surrounding our galaxy is a ghost from a forgotten collision. The European Space Agency's Gaia spacecraft, tasked with charting the precise motions of over 1 billion stars, has uncovered the remains of a dwarf galaxy that the Milky Way consumed long ago. Astronomers have named this relic Pontus. It is not a visible structure, but a subtle statistical signal, a family of stars moving together through the galactic halo with a shared velocity and chemical identity that mark them as outsiders. These stars are ancient and metal-poor, a signature of a small, primitive system that formed in the early universe and lived in isolation before its fateful encounter with our far larger galaxy. Gaia's extraordinary data allowed scientists to pick out this coherent stream from the chaotic background of halo stars, tracing the final orbit of Pontus as it was pulled apart by tidal forces. This stellar stream is more than just debris, it is a fossilized timeline of galactic cannibalism. By modeling the orbits of these stars backward, researchers can estimate when the merger occurred, placing it among the earliest major accretion events in the Milky Way's history, a foundational moment in its growth. Each star in the Pontus stream carries a chemical fingerprint distinct from the Milky Way's native population, telling us about the conditions in its original, smaller home. Studying this fossil allows us to perform a kind of galactic archaeology, reconstructing the properties of the original dwarf galaxy and the violence of its assimilation. It confirms a long-held theory that large galaxies like our own were built over cosmic time from the mergers of many smaller systems. Pontus is one of several such streams now being identified, each a chapter in our galaxy's autobiography written in starlight. These silent rivers of stars are the evidence of a violent past, showing that the serene spiral we see today is the product of a long and turbulent history of collisions, each one adding its own unique stars to the great galactic tapestry. These 25 phenomena are not isolated curiosities, but a chorus of voices all telling the same story. our universe is far stranger, far more dynamic, and far less settled than we ever dared to assume just a generation ago. Each discovery, from the lonely galaxy in the void to the ancient chemical fingerprint of a first star, represents a direct challenge to our existing models. They are not minor adjustments, but fundamental questions written across the sky. We built our cosmic rulebook from the calm, mature universe we could easily see, but new tools are now revealing the frantic, chaotic youth that shaped everything. The James Webb Space Telescope, with its infrared eyes and facilities like the ASKAP radio array, are not just giving us sharper pictures, they are opening entirely new chapters in a story we thought we knew. They allow us to witness planetary systems being sculpted in real time, to find black holes that should not exist so early, and to detect the faint whispers of structures that defy classification. Two of our most foundational concepts, dark matter and black hole formation, have been thrown into beautiful turmoil. The galaxy, seemingly without dark matter, forces us to ask if this invisible scaffold is truly universal, or if nature has more than one way to build an island of stars. The overmassive black holes in infant galaxies scream that our timelines for cosmic growth are far too slow, pushing us toward radical ideas like direct collapse black holes born from primordial clouds. Even the humble exomoon candidate and the nomadic JWST worlds insist that planet formation is not a single, tidy process confined to stellar disks, but a prolific and diverse art form practiced across all environments. Every contested claim, like the phosphine on Venus or the nature of the Great Cold Spot, is equally vital. They are the sound of the scientific process in action, a rigorous, collective debate that separates fleeting hope from durable truth. This friction is not a sign of failure, it is the engine of progress. What emerges from this cascade of new data is a profound shift in perspective. We are moving from a universe of fixed categories to a cosmos of continuous transformation and hidden populations. Black holes can be ejected, stars can be flung into the void, and entire galaxies can live and die in darkness. The frontier of discovery is no longer just at the edge of the observable universe. It is in the subtle anomalies in our own backyard, in the unexplained flickers from the Galactic Center, and in the ancient chemical memories of the first stars. The next great revelations will come from connecting these dots, from using these 25 puzzles as pieces to build a new, more complete, and undoubtedly more astonishing picture of reality. This journey has no final destination, only a horizon that recedes with every question we answer, revealing 10 more in its place. Your curiosity is the most essential instrument in this endless exploration. Stay engaged, stay wondering, and look up. The cosmos is rewriting its story, and we are all here to read it.